All right, so this is our Unit 5 Physical Behavior of Matter review sheet. Number 1, a sample of solid carbon dioxide and gaseous carbon dioxide would differ in their physical properties. They would have the same molecular structure, so it would not be choice 3. And then 1 and 2, I think, are more sort of like nonsense. But they would have different physical properties because the solid would be vibrating in a regular geometric pattern and the gas would be moving in random directions. All right, number 2, we have what is clearly a heating curve, and it's also an endothermic heating curve because as time is going forward, the temperature is increasing. So we have an endothermic heating curve. But this question only asks about section AB, and during section AB, the temperature is not changing. You can see this flat line for the temperature. So that means that the kinetic energy is going to remain constant and the potential energy would be increasing. So of the answer choices I see, number 1 definitely stands out to me as being correct. All right, so in number 3, they're asking us to identify the phase change that represents sublimation. And sublimation is when you go straight from the solid form of a substance to the gas form, skipping the liquid phase. So of the choices that I can see, choice 2 matches that definition. For number 4, I'm asked which temperature is equal to 120 Kelvin. So on your reference table, you'll see that Kelvin is Celsius plus 273. With algebra, that would just mean that Celsius is Kelvin minus 273. So if I want to know the Celsius equivalent of 120 Kelvin, I can just do 120 minus 273, and I'll get my Celsius version. That is going to be negative 153 degrees Celsius. All right, number 5. We have a 36-gram sample of water, and it has an initial temperature of 22 Celsius. After the sample absorbs 1,200 joules of heat energy, the final temperature of the sample would be. This is going to be a Q equals MCAT question. And they're asking me for the final temperature of a substance. But what I'm actually going to solve for is the change in temperature, and then we'll figure out the final temperature from there. I rearranged my equation to solve for delta T, and it says Q over MC. The amount of heat that was stated in the question was 1,200 joules. The mass stated in the question was 36, and the C is the specific heat capacity for water. It's referenced on table B as 4.18 joules per gram Kelvin. I'm getting a value of 7.97 degrees Celsius of temperature change. So if you start at a temperature of 22 and your temperature changes by 8 degrees Celsius, you could end up at 30. So 3 is my answer. All right, so continuing on to number 6. We have the temperature of a sample of water changing from 10 to 20. When the water absorbs 420 joules of heat. We want to know the mass of the sample. This is going to be a Q equals MCAT question as well. But we are solving for M, mass of the sample. So I rearranged the equation so that it says M is Q over C delta T. And now I can plug in my variables. I have a heat of 420 joules. The specific heat capacity for water is 4.18, and the change in temperature is 10, and that's meaning that we went from 10 to 20, so the change is 10. And I'm getting a value of 10 grams. All right, number 7. When 200 grams of water cools from 50 to 25, the total amount of heat released is. This is also a Q equals MCAT question, and we are solving for Q. So let's plug in the variables that we need. The mass is going to be 200. The specific heat capacity for water is 4.18. And the delta T is from 50 to 25, so that's 25 degrees of change. And we'll just need to find the product of those numbers. And I got a value of 20,900 joules. This could be represented in kilojoules, and that would just mean dividing it by 1,000. So 20.9 kilojoules could be rounded to 21 kilojoules. So I'm going to go with choice 2. All right, number 8. What is the minimum amount of heat required to completely melt 20 grams of ice at its melting point? So when they use the word melt, they are signaling to me that I'm going to use the equation Q equals mHF. HF is for melting and freezing. So they used melt, so I'm going to use HF. And they do want heat, so we don't need to rearrange it. It's already set up to solve for heat. The mass is 20 grams, and the heat of fusion for water is 334. So when I find the product of those two numbers, I'm going to get 6,680 joules, or choice 3. All right, so for number 9, how much energy is required to vaporize 10 grams of water at its boiling point? So the word vaporize means that we're going to use the equation Q equals mHV, because HV is for boiling and condensing. So since we're looking for Q, we don't need to rearrange anything. The mass is 10 grams, and the HV is for water, so that's going to be 2260 joules per gram. And that's going to give you a value of 22,600 joules. We might need to report that in kilojoules since it's so large, so divide by 1,000, and you'll get 22.6 kilojoules. So for number 10, we have a sample of chlorine gas at 300 Kelvin and 1 atmosphere. At which temperature and pressure would the sample behave more like an ideal gas? So gases, you can promote ideal behavior from a gas by increasing its temperature and decreasing its pressure. So we would want to increase the temperature above 300 and decreasing the pressure below 1. So I think that the best answer choice I can see for this one is 4, because 600 represents an increase in temperature and half an atmosphere represents a decrease in pressure. So for number 11, according to the kinetic molecular theory, which statement describes the particles of an ideal gas? Ideally, gas particles are, they have no attraction for each other, and they are arranged they're moving in random straight lines. So I would say that choice 1 and 2 are out for that reason. They're not moving in constant circular motion. That's just silly, so it's not 3. But number 4 says that the collisions of the particles result in the transfer of energy, and this is directly pertaining to one part of the kinetic molecular theory, which is stated as elastic collisions. So 12 is similar to number 11 and number 10. It's about ideal gases, and the best conditions you can put a gas under to make it behave ideally is to give it large temperature and low pressure. So of the choices I'm seeing, number 3 looks pretty good because it has a relatively large temperature and low pressure for the 4 choices. All right, number 13. Which rigid cylinder contains the same number of gas molecules at STP as a 2-liter rigid cylinder containing hydrogen gas? We're going to use something called Avogadro's hypothesis to answer this question. And it simply states that if you have 2 samples of gas at equal pressures, volumes, and temperatures, that they must also have equal numbers of particles. So if I apply that hypothesis to this question, I can see that a 2-liter cylinder of hydrogen would have the same number of gas molecules, assuming that our standard temperature and pressure is in place. It would have the same number of gas molecules as an equal volume of another gas. So while we have 4 different gases listed, the identity of the gas doesn't matter. It's only the volume of the gas that matters, which is why choice 2 is the answer. We have a 2-liter cylinder of methane. So in this next question, we have a 220 milliliter sample of helium gas in a cylinder with a movable piston at 155 kilopascals of pressure and 265 Kelvin as the temperature. But the new set of conditions will be a new volume of 95 and a new temperature of 310. They're asking for the new pressure. There are no shortcuts around this one. It's a pretty standard combined gas law question. And we are looking for pressure 2. So I'll rearrange the equation to solve for that. Using inverse operations, you'll need to divide both sides by V2 to cancel the V2 on the right, and you'll need to multiply both sides by T2 in order to cancel the T2 on the right. And I'll rewrite the equation in its new form. So there it is. At this point, I can plug in the values that I know. So P2 is going to be equal to pressure 1, which is 105 kilopascals, times volume 1, which is 220 milliliters, times temperature 2, which is 310 Kelvin, over temperature 1, which is 275 K, and volume 2, which is 95 mils. After performing those operations, I got a value of 274 kilopascals. Number 15 is also a combined gas law question, but we'll be able to remove temperature, and here's why. We have a 25 degrees Celsius sample of gas, which we would convert to Kelvin, but it does say that the temperature is held constant. And since temperature is held constant, I'm going to omit that from the equation. So I'll write the equation now. So it was the standard gas law equation, but I crossed out my temperatures, and I'm left with P1 V1 is P2 V2. I can see from the question that they're asking me for the new pressure, or P2. So I'm going to isolate for P2 using inverse operations. I got P1 V1 over V2. Pressure number 1 is 125 kilopascals, and volume 1 is 145 milliliters. Volume 2 is 80 milliliters. I'm getting 227 or so. What would that be? That's a pressure, so kilopascals. And I'm assuming from the answer choices that we can round it to 230 safely. All right, number 16. It says, which temperature change would cause a sample of an ideal gas to double in volume? So in order to double the volume, what you could do is you could cut the pressure in half, or you could double the temperature. The one that's going to make the most sense for this question is to double the temperature because the answer choices are all in Kelvin or Celsius. We would need to double the temperature, so we can automatically remove choice 1 and we can automatically remove choice 3 because those are halving the temperature. But choices 2 and 4 will confuse students because they appear to be the same thing. However, I also will remove choice 4, and the reason for that is because when you increase the temperature from 200 Celsius to 400 Celsius, you have not actually doubled the temperature. Remember that 200 Celsius is not 200 degrees above absolute zero. 200 Celsius is more than 400 degrees above absolute zero. So you're not doubling the temperature when you go from 200 to 400, you're increasing it, but you're not doubling it, and that's because absolute zero is not at 0 Celsius. On the other hand, absolute zero is at 0 Kelvin, so when you go from 200 to 400, you are observing a direct relationship between kinetic energy and temperature. So doubling the temperature from 200 Kelvin to 400 Kelvin does actually double the temperature in general. So the best answer is choice 2. And so for 17, we have a rigid cylinder of gas at STP, and we need to know the pressure after it has been heated to 410 Kelvin. Since this gas is in a rigid cylinder, its volume is not going to change. So I'm going to remove the volumes from the equation because volume is constant. And we're left with P1 over T1 is P2 over T2. We are looking for the pressure of the gas, so we're looking for P2. I'm going to use algebra to isolate that. I was able to find that P2 is going to be P1 times T2 over T1. And I can plug in variables now. The first pressure is standard pressure, and that could be either in atmospheres or kilopascals. But looking at the answer choices, the ones that they're listing for the second pressure are all atmospheres. So that means I'm going to list my P1 as the standard pressure in atmospheres, which is 1 atmosphere. T2 was stated as 410 Kelvin, and temperature 1 is standard temperature. In Kelvin, that's 273. After a quick calculation, you'll find that the second pressure is going to be just about 1.5 atmospheres. So choice 4 is my answer. For number 18, it's really just testing the definition of a solution as a homogeneous mixture. Therefore, choice 3 is the strongest answer. For number 19, we have a mixture of sand and table salt, and we want to separate them using filtration or a sieve. And we are able to separate those two particles based on their solubility in water. What the question is implying that you would do is you would take the mixture of sand and salt and pour in some water before you did the filtration, and the salt would dissolve in the water, the sand would not. And when you filtered that substance, the sand would stay in the filter paper and the salt water would come through. So you're separating them based on their solubility in water. To help explain that, I'm drawing a quick particle diagram. Basically, I'm using a key of black dots for sand and red dots for salt. The water is indicated by the squiggly line. So you can see that the salt is evenly dispersed throughout the water. That's because salt is going to form a homogeneous mixture with water. Sand would form heterogeneous mixture with water because it doesn't dissolve. And when you pour this solution through a filter, the homogeneous part would flow through the filter and the heterogeneous part would stay behind. This is getting at a really important concept, which is that homogeneous mixtures cannot be separated using filtration, but heterogeneous mixtures can. So I'll zoom back out before I write that so you can get some context there. And there you go. Lastly, number 20, petroleum, which is the crude form of oil, can be separated by distillation because the hydrocarbons, these are the different types of substances that are in the oil. They can all be separated from each other because they have different boiling points. They're not elements, they are compounds, these hydrocarbons. So compounds with different boiling points allow us to do distillation. Specifically, this kind of distillation is referred to as fractional distillation. And that concludes the review for the Unit 5 exam. Good night and good luck.